Hello, I am Theo Héral. I am going to present our work on Temporal Stochastic Softmax, a training method for 3D convolutional neural networks. For practical reasons, to reduce GPU memory consumption and computation time, spatiotemporal deep learning models are trained with short video clips randomly sampled from training videos. Clips are sampled uniformly, which is equivalent to using average pooling on classification scores. In inference mode, as gradients are not required, the classifier is convolved over the entire videos, and average pooling can be used. However, literature has shown that all clips are not equally relevant. Training with short clips introduces several problems. The video labels have to be broadcast to the corresponding training clips. Typically, in emotion recognition, we consider that all clips extracted from a video labeled as happy will belong to this emotion class. As we can see on these examples, the video label is not always meaningful at the level of a clip, and this will introduce noise in the training process. The video label will not correspond to clips with occlusion or which do not capture the emotion apex. We can see the same issue on the task of pain detection. Pain expressions are very localized in time, and some clips only contain neutral expression. More generally, the issue is that all clips are not equally relevant to training and to the classification process during testing. To address this issue, a weighted temporal pooling mechanism has the advantage of focusing on the most important parts of the video, while inhibiting less relevant frames. However, weighted pooling cannot be implemented during training because 3D CNNs only process a single clip at a time. Our solution is to design the temporal weighting mechanism within the clip sampling framework. This way we can avoid training on irrelevant clips and reduce noise in the training process. We choose a weighted pooling mechanism based on the softmax function for its adaptability. To apply softmax pooling at the video level during training, we use a weighted sampling mechanism. This training method is referred to as Temporal Stochastic Softmax. The principles are the following. The relevance of a clip for training and inference is measured as its classification score. Clip scores are evaluated iteratively throughout training to estimate temporal distributions over entire videos. At every epoch, training clips are selected with a softmax strategy based on their scores. With weighted sampling, the importance of a clip in the training process is implemented as a frequency of selection. In expectation, the result is equivalent to applying a softmax layer on the score sequence of the entire video, which is not possible in practice as we saw earlier. Also, with weighted clip sampling, computation is not wasted on irrelevant clips. The training process is split in 3 phases to facilitate the joint process of selecting clips and updating distributions: warm-up, exploration, and weighted sampling. Here is an example of the weighted training process. For 3 epochs of warm-up, we sample clips randomly because the classifier produces random outputs. Then, for 5 epochs, we select training clips evenly spaced in time to cover the entire video and get a good estimate of the temporal distribution. When a clip is used for training, its classification score for the target class is used to update the temporal distribution of the video. After this exploration phase, we use a softmax strategy to sample relevant video clips for efficient training. We keep updating the distributions with new information throughout training. We experiment with Temporal Stochastic Softmax on a small C3D and an inflated 3D VGG16 model. Our method is validated on emotion recognition and pain detection benchmarks, with consistent improvement over the uniform sampling baseline. With Temporal Stochastic Softmax, we designed a method to efficiently train 3D CNNs for spatiotemporal recognition with videos of arbitrary length and sequence level labels.